Hello, I'm Federico Figari Tomenotti from MaLGa, University of Genova, and I will present a method to estimate the 3D pose of a person from images with an application to social interaction analysis. I start from the motivations and the general idea behind the work. The task of understanding the gaze direction of a person is very relevant in a number of application domains, ranging from HRI to social interaction analysis. However, the gaze is sometimes hard to be understood depending on the viewpoint of observation. A more robust proxy is the 3D head pose. We start from a small set of face keypoints detected using any pose estimator that are provided as input to an heteroscedastic neural network to estimate the 3D angles representing the pose associated with three uncertainties. The architecture is very light and allows us to provide robust estimation with a limited computational demand. Here is a sketch of our architecture. The input is composed by the x and y pixel coordinates of the facial keypoints plus their confidence, provided by the pose detector. The coordinates are centered and rescaled to be in 0, 1. Points coordinates and confidences are processed independently using a 1D convolution plus a flattening, and then they are combined to be provided to the second part of the architecture, made of fully connected layers. The output is represented by three angles, yaw, pitch, and roll, plus their corresponding uncertainties. We use the multitask loss reported in the slide that incorporates a term taking into account the uncertainty. Each task is denoted by high, and corresponds to the estimation of an angle. The uncertainty is learned as the logarithm of the variance of a normal noise distribution. The uncertainty that we consider captures the noise in the input, which in this case may be due to missing or incorrect detections. These can lead to difficult viewpoints or occlusion problems. In the picture, we show the uncertainty measures from a video sequence where a person moves the head in different directions, thus offering different test poses to the method. It is easy to observe that for some poses, the ones associated with ambiguous views or missing detection, the uncertainty tends to be higher. A couple of qualitative results to highlight the properties of the uncertainty. On the left, we have a cumulative plot where we show that the average error of the angles estimates increases accordingly to the uncertainty. On the right, instead, we show the dependence of the uncertainty on the number of input keypoints. In particular, the more keypoints we have in input, the lower is the uncertainty in the estimates, as we can intuitively expect. Notice that randomly dropping the keypoints to perform the experiments lead us to generate highly variable configurations, including some very rare configuration in practice. The quantitative evaluation has been carried out using two protocols used in the literature. In P1, the architecture has been trained on the 3000 WLP dataset and tested on the BWI dataset. In P2, training and tests have been performed on the same dataset, that is BWI. As you can appreciate, our method performs in line with the top two methods, but with a computational reduction of more than one order of magnitude with respect to the best one. We show a test-bed scenario in which the method has been applied to the problem of layout detection, which aims at detecting pairs of people looking at each other as a cue of social interaction. The methodology is fairly simple. After retrieving the 3D head poses of people in the scene, we used a geometrical reasoning to derive for each pair the measures of layout, which derives from the cosine of the angles between the head direction projected onto the image plane, reported in blue in the image, and the line joining the heads in white. In this task, as reported in the table, our method achieves a very good performance. And that's all. Thanks for your kind attention.